I think we just get started here with Ohad telling us a bit about the semantic foundation of cost synthesis. Please.
Thanks. It's always a pleasure to be at HOPE. So this is very much ongoing work I started doing with Georg quite recently. So the main purpose is to initiate the hallway track to see what else we could be looking at. And this talk has two parts. One of them is very technical. That's probably going to be on that hallway track. We're not going to have enough time for it. So I'll stop in the middle to take more questions, and then we can see if we need to get to the more technical bit. So let's go back to maybe year 1 CS, if you've done computer science in university, maybe year 2, where you're looking at the complexity analysis of data structures. Okay, so what's a data structure? It has two parts. It has the user-facing bit, which comprises of some operations, and then it guarantees some complexity bounds on these operations. So if you use a single operation lots of times, maybe, and you know that it's cheap, then it's not going to be too bad for you when you try to do something real with it. And then behind the scenes, there's an implementation of that data type or that data structure using a data type, maybe with some semantic invariants, with some functions that would satisfy whatever behavior you expect in all that operation. So that's very abstract. Let's look at an example. The classic example is a stack, right? So we have a stack where we're putting in elements into it, and then we take them out in the reverse order. So we have two operations, a push, that here we push the value 3 onto the stack, and here we have a multi-pop that pops 3 elements, and we get back the top 3 elements that used to be here. So in the picture, okay? So that's all nice and clean, year 1. And then you want to analyze kind of the bounds that these data structures guarantee. So the worst case analysis, you say, well, to push, usually I can do it with one insertion, and to pop, I'm going to need at least k deletions, unless I'm doing something really, really clever behind the scenes. And what Tarjan noticed in '85, following a bit of other work on aggregate complexity, that usually the worst case is too coarse, right? We don't care about just a single operation in isolation. We care about a bunch of operations. Okay, so you want to have a slightly more refined analysis of how much will it cost to do a sequence of operations in the worst case. Okay, and what you can notice about this example is that if I do a sequence of n operations here, the total cost is going to be 2n insertions and deletions. Because every time I insert something, right, I can remove it at least once, at most once. Okay, so the cost of the deletion is bound by the number of insertions. So the total cost is going to be bounded by the number of insertions plus the number of deletions. Okay, so I can actually make this reasoning more local by assigning fake costs to each operation. Each push now costs 2 units. Okay, and the pops are for free. Right, because I already paid for them when I inserted. Okay, so these costs are completely imaginary, right? These amortized costs, that's what they're called. But the point is that when I take them together, I can bound the worst case cost for the sequence. Okay, so far so good. Great. And this is this little proof of why the amortized cost, just summing it up, bounds the actual cost. Great. Okay, so Tarjan in that same paper introduces the potential method, which is a slightly more compositional way of showing this. Okay, and the way you do it is by associating some costs to the data structure, okay, in a way that would kind of cancel out. So let's see what happens here. We're kind of coming up with two kinds of costs. One is the amortized cost for the operation, so what will become the amortized cost for the operations. It's just one ingredient. And one of them is a potential for the data structure. Okay, so you're storing in data type some cost. Okay, and as you operate on it, so you you take the value of the data structure, you operate on it. It has some potential, and then you want to establish to show this inequality, which looks a bit weird. Okay, when you phrase it like this, but if you think about it in this way, it makes a little bit more sense. So what it says is that if I look at the difference of potential from before I've done the operation and after I've done the operation, okay, then that bounds the difference, the discrepancy between the amortized cost and the real cost. Okay, so I've done some operation, it costs k units, maybe my amortized cost is 0, there's some discrepancy. Okay, I make sure that that discrepancy is bounded by the potential difference. Okay, and then when I do the sum, it will cancel out with a telescopic argument. Okay, so if you've never seen it before, it's very pretty. If you've seen it before, you already know about it. Okay, but really, if you write it on the back of an envelope, then it would work out just like this. Okay, so I need to do, I want to bound n operations. I start with my potential at the end, okay, and then I can telescopically move things to the other side using this inequation. I get the amortized cost plus the initial potential, and I move things around. I get the bound I wanted. Okay, so it's a very pretty argument, again, due to Darjan. Okay, so what is this talk about? Okay, so there's a line of work when you want to do this more formally, maybe in an automated or interactive way. So the keyword is amortized analysis of resources, A cubed R. I think Jan Hoffman calls it amortized resource analysis. So automated amortized resource analysis. So that's AARA. I swapped it because it looks cooler with a superscript, right? Okay, so it starts with Martin Hoffman, right? And then Stefan Jost and Jan Hoffman, spelled differently, note the spelling, from the 2000, and we have like 20 years of this, and there's a very nice survey paper, I think from last year or 2 years ago by Jan and Stefan, really talking about a whole bunch of systems. Okay, so kind of the premise there is you have your operations, you kind of declare the types, the data type implementation, you implement a language not too different from, say, ML or some object-oriented language or Java. And then you hit a button, and then it goes off and computes and comes back with some complexity bounds on your methods. And in the deterministic case, this is maybe not too exciting because we have the textbook bounds. But if you start adding, say, probability, then the exact probabilities in which you go one side or the other side in other structure start to matter in terms of the bounds. And if you balance it this way, then you get very good bounds, and otherwise it kind of just diverges and you get horrible complexity. Okay, so you might want to do it interactively. But that's the dream. I think we're not exactly quite there yet, but hopefully we'll get there. Okay, so what's the architecture of these systems in a very kind of bird's eye? You have your cost model. Okay, so you write a little implementation for your operations like push XS, you const X on top of the list implementation of the stack. Okay, and then you pay some cost, right? So your cost model is a program that at any given point tells you how much this operation costed. Okay, that's what I mean by a cost model. Okay, and it looks like maybe an effectful type lambda calculus with some cost modeling primitives. So you stick it into the analyzer, it goes and churns, maybe calls some SMT solver on the side. Okay, and out pops the same program with maybe resource usage annotations on top of it. Right, that say something like push has amortized cost 2. That's the dream. Okay. The original language with the cost primitive has a cost semantics, and you show that whatever comes out, if it satisfies the constraints that you fed into the SMT solver, the constraint solver, will actually bound the cost of running the program. Okay, so that's kind of the bird's eye of how these systems work. Okay, and kind of the way this works under the hood, kind of the workhorse of this, and we've seen an instance of it earlier in Satoshi's talk, is the kind of the weakest precondition semantics, right? But with a quantitative flavor. Okay, so you have these kind of, you think of the annotations as whole triples, and then you have rules for propagating the annotations through your program, subject to some constraints. If only you could satisfy those constraints, everything will be okay later. And this, of course, builds on a long line of work started by Cozen and MacIver and Morgan about this kind of weakest precondition. I think Carol Morgan called these pre-expectations, which I think is not the best way. Yeah. So I'm not going to call them that henceforth. But the work is fantastic. Okay, just not the name. Okay, so this is kind of a quantitative weakest precondition calculus. Okay, and the point is that these annotations are synthesized by the solver, and the constraints guarantee the soundness. Okay, so you kind of have to design everything so that everything lines up. Okay, so kind of the motivation for why we started looking at this is this atlas system by Georg and Lötgeb and Zölge, where they worked on probabilistic data structures, where I said that the balance of probability matters for you getting good amortized costs. Okay, where they could automatically deduce quite tight bounds, tighter than known bounds even, for randomized data structures, randomized splay trees, randomized splay heaps, meldable heaps. And they did by using very sophisticated annotations, so hereditary ranking functions with polylogarithmic cost functions. So they look like this cryptic tuple where you have a ranking as q and p1 to pn are some other coefficients, but what I mean is some kind of a polylog logarithm in the size of the tree and in this kind of rank of the tree, which is a proof theoretic quantity taken from ordinal analysis. Georg, in his past life, was a rewriting person from the Vienna school, so he knows a lot about these things. And with this, they could establish tight bounds on these data structures, but it was very, very brittle. Okay, so for example, if you say, okay, that system only supported binary trees, okay, with the invariance of being binary search trees. If you say, okay, let's look at, say, lists and call it as spines, then suddenly everything kind of breaks down. For example, it cannot synthesize this amortized cost of 2 properly. You get log in the size of the tree, which is way, way too much. Okay, so his perspective is, okay, we have this sophisticated system that generates these tight bounds, but the moment you switch things, everything, it goes down the drain. Maybe we can understand a bit better what's happening there and make it a bit more flexible. So that's what we're trying to do here. Okay, and this is very early days. Okay, so kind of why that's happening? So there's this design tension, right? So on the one hand, you want really tight bounds. So you want to have a kind of a DSL for the quantities that's very, very expressive. Okay, so that one, the reason it kind of fails is you only have these logarithms and you kind of have to make something a bit bigger, then it gets too big and so on. And you have to propagate the constraints throughout your program and convey that to the SMT solver. Everything is kind of a balancing act. Okay, so the explicitity of the actual language need to be constrained, the explicitity of the quantity language. Okay, so you have to balance this trade-off. And on the other hand, right, that should be, no, that's fine. Okay, so if you want to, rapidly get tighter bounds, right, by rapidly prototyping the different annotations, right. If you want to guarantee soundness, like having this whole proof of the whole system, right, kind of agrees on both the cost semantics and this round trip to the SMT solver, that's a lot of work. Okay, so you want to maybe short circuit that so you can explore various different notation systems for your amortized costs. Okay, so that's another trade-off, right? The more you prove about it, the slower it is, and maybe we can do some more work up front. Okay, so what do we propose, right? We propose this kind of a, I don't know, maybe the buzzword would be a nanopass architecture, right? So we have kind of a stacked architecture, right? But each layer is doing something very specific, and apart from the last layer, we can kind of do everything below it wholesale up front, and then just change the top layer. That would be the dream. Okay, we're nowhere near that, but we think we might be. So that's the point of having the talk here. Okay, so at the bottom layer, you have to have some programming language, and of course, and a chunk of what we've done is carve out a language that's expressive enough to be able to talk about the programs that we want to analyze, but not too expressive that we can't even dream of propagating those constraints to the SMT solver. So for example, this CPS translation that Satoshi was talking about, that's way too much. It's very difficult to reason about automatically in that way, right? You have to do it interactively, maybe in the context of the hearing prover, I think, but we can talk a bit more about that later if you want. Okay, so you have some language, and in the hallway track of part of the talk, I can show you exactly what language that is. Okay, and it has the universal semantics given by some kind of a Kleisli arrow. So given the inputs, I'm going to do some monadic computation and return the result and the cost of the program. In this case, this monad is kind of a fancy probability monad. Okay, it's not that fancy. It's okay. Not too posh. Okay, and then you show at this level, right, that it's adequate. So that means whatever you prove denotationally about it, then follows something operational about it. Right? So you kind of do the one part of the heavy lifting for soundness first. Okay, and you can do that in general. The next layer is a logical spec layer. I'm actually not going to talk about it today, but for example, when you talk about binary search trees, there's a semantic property there saying that everything on the left of the left child has to be smaller than the node, and everything on the right needs to be not smaller than the child, than the node. And of course, in order to specify that, you use a whole bunch of functions. For example, say in red black trees, you might be counting the number of nodes, red nodes and black nodes, and therefore that information might be useful for the SMT solver when you try to synthesize bounds, right? But so we do want to include it, but and so we're leaving the room for that. But we're not. I'm not going to spend more time talking about it today at all. It's secondary to what we're trying to do. Next comes kind of the meat of it. It's a quantitative layer where we have. I don't want to call them expectations. I'm going to call them estimates because these are things you estimate. You can call them integrands if you're not scared of the word integral. Some people are. Okay, and then you make assumptions about two estimates being in one bounding the other, and then you guarantee that two different estimates bound the other. And what that gives you is a kind of a weakest precondition semantics, but with a quantitative structure. And what Satoshi was talking about is the fact that we have this kind of cost estimate, right? That we can, of course, express semantically, but sometimes if you're working completely syntactically in the logic, you want to expose syntactically, right? So a syntactic construct gives you the weakest precondition. And this is what this cost estimate is doing. Okay, so what we'll do is we're going to show that something bounds the cost. Okay, and that's going to be in the one layer up. And this is the thing that you want to start replacing all the time. Right, you're generating assertions in this analysis layer that talks about some notation about potential and some notation about amortized costs, and then you show how it translates down into the quantitative logic part that you have already proven sound. So all you have to do is show that the soundness of constraint holds at this level. And now we can start properly prototyping this. Yeah, so this is what we want to do. What we've done is just this. Yeah, this is the point of a workshop talk. This is still quite a lot of work because we had to transport a whole bunch of stuff from existing work, make it all fit, and so on. So it's not nothing, but it's also not a lot, I think. How am I doing for time? Because
you're on time, but we're a little behind.
Yeah, I know exactly. So that's why. So I think I will do what I said now. I'll stop here.
Right.
Okay, and take questions.
All right. Let's thank the speaker. Do we have any questions? Yes.
So you talked a bit about, this is more a question about Atlas than anything else. Mm-hmm. You talked a bit about relying on an SMT solver to do things automatically. You also mentioned that it had support for things like logarithmic ranking functions, and I thought that took you out of the SMT decidable fragment.
Oh yeah, it's very clever. It's not shipping in logarithmic constraints. It's using like Farkash's lemma to bound them in a different way, and it's shipping off more like integer bound problems and so on. Yeah, there's a lot of cleverness that goes into it, which is why it's good to give yourself room to think, right? So you can kind of go out of those annotations. Sorry, I preempted your question. Is that
Yeah, no, that answers the question.
Okay, thanks.
All right. Any other questions? Otherwise, I can maybe ask one. So you have the language. You talked a little bit about the expressivity of the language. Can you maybe tell us a little bit more about the language and how expressive it actually is?
I can show you the language if you want. This is the language. So it has two components. So you have algebraic data types. Okay, so you have sums on products using this is row notation. I think we've seen a version of it earlier. But you only have ground data types, so no functions at the recursive calls. And then the language is a first-order language. Okay, so you can call functions, you can declare those functions, but the functions are going to be first-order. So they're going to take ground types, they're going to return a ground type, but they can be mutually recursive. Okay, but otherwise you have pattern matching, and then you have the cost modeling primitives, and then probabilistic primitives, also sampling from any countably supported distribution. Yeah, that answers your question?
Yes, thank you. I'll just check how we're doing for time.
We can get coffee early, I'm happy with that.
Yeah, well, we are right on time, actually, so maybe we should really take Ohad up on his office doing a hallway version of the talk.
Yeah, happy to.
Yeah. All right, let's thank the speaker again.